Up next in the series here is DK Panda from the Ohio State University, who will be presenting designing high performance and scalable middleware for HPC, AI, and data science. DK, it's great to see you again.
So good afternoon, everybody in the East Coast. Still in the good morning in the West Coast. So I'll be very happy to share here some of the latest things what we are doing. The title is Designing High Performance and Scalable Middleware for HPC, AI, and data sciences. As most of you know, I mean, we are in a very exciting phase. I mean, these data are from top 500. Jitin showed some of the numbers. We still have the number one system as the Fugaku, but the whole community is waiting for the exaflop systems to arrive. And as some of you would have heard, Oakridge National Lab made an announcement saying the new frontier system with Slingshot and AMD GPUs will be operational by January 1st, 2023. So we hope to see in the next 9 months, unless some other machines comes up and then gets announced in the ISC, we'll see where this new machine is coming. And in this context, as you know, it's not only the traditional HPC, but we have a lot of focus on deep learning, machine learning, the data science. So there is a lot of convergence is happening. When we try to design these kind of systems, can we try to design some convergent software stack so that if people are coming up with workflow, which has HPC component, AI components, and data science components, they can actually mix and match here. So this is where in my group, we have been aiming to design this kind of convergent software stack. I'll share some of our experience here. And not only we want to address it on the on-premise, but also we want to address it for the cloud. So this is where my talk will focus on the MPI-driven middleware. To this community, most of you know the MPI has been there for many years, which is the message passing interface standard. And anytime a new machine comes up, you have a very good high performance design of the MPI library for that system, even including all the cloud. So then the question is, can we leverage that? And not only try to run the traditional scientific applications, but we can also run AI application, data science application, and big data. So in that way, we'll be able to very quickly provide solutions to all these environments. So in this context, today, I'll be trying to I'll start with the Mapis project. Many of you in the community might be familiar with that. I'll try to focus some of the very latest numbers we have on the latest networking technologies with both CPU side and GPU side. I'll also focus on how we are trying to take advantage of the new DPU architectures for offloading and accelerating applications. And then I'll try to talk a little bit about the high performance deep learning and machine learning stack, which we have designed on top of the MPI, and how we are able to use that to deliver good performance for a lot of machine learning and deep learning applications. And then I'll talk a little bit about the, in addition to what we have been doing from the OSU side, we're also trying to provide a lot of commercial support and value-added products from a commercial startup called Icicle Solutions, who is a sponsor also of this conference. I'll talk a little bit about this. And then I'll try to finalize. This is something new. I have not talked in this venue earlier. Last year, we have been funded a new AI institute from National Science Foundation. It's called Icicle. It's a $20 million investment. I am the overall PI, but there are almost like 50 researchers from 14 universities are involved to really take the field of HPC, AI, machine learning, deep learning to the next phase by 2030. So I'll try to give you an overview of that project. It started in November 1st. We are into like almost finishing the first 6 months, but I'll just try to give you an overview. And in the future, once we have some better solutions available from this institute, I'll be very happy to share those things. And then I'll conclude. So as many of you know, this the MapisToDPU project, if you're not familiar, we started almost in the day one of Infiniband. Infiniband, if you remember, October 1st, 2000, it was introduced. So prior to that, we were working on technologies like Mirinet, Quadrix. Those were proprietary solutions, but Infiniband came as an open standard. And we're the very first one in the world to really jump in and explore how the new kinds of mechanisms and features of Infiniband can be utilized in the MPI level. And then we worked at that time very closely with Mellanox and a lot of other Infiniband vendors. We had our first MPI demonstrated at Supercomputing O2 almost 20 years back. And then since then, we have been evolving. This is like a 21 years project. I'm very happy and proud of my team members who have been working almost for 21 years with all the students and staffs. So we have been evolving over the years, not only with Infiniband, over the years, we have moved to Omnipath, iWarp, Rocky, AWS EFA. And with the very latest release, I'll talk a little bit about, we also support the Rockport Networks and also Slingshot. And then, of course, we have been providing support for all the CPU, GPU platforms, and very latest also the DPU platform. So this library is currently being used by more than 3,200 organizations in 89 countries. Just from our website, we have crossed like a 1.5 million downloads, and it's steadily growing every day. And not only is this just the download from our site, but MapisToDPU library is a part of all the different distributions, Red Hat, SUSE, OpenHPC, SPAC. We don't keep track of those distributions. But in addition to that, we have been empowering a lot of top 500 clusters all over the years. We have been in this community for the last 16 years and pushing the frontier. So this shows the overall architecture of our MapisToDPU library. As you can see on this side, these are the, anytime a new networking technology comes up, our main interest is to really explore the new mechanisms, the features, and how you can leverage that into the MPI layer using newer kinds of mechanisms. And that is from the networking side, and this side is also the CPU, GPU, and then the DPU perspective. And once we publish these papers, typically in 6 to 9 months, we are able to actually take those designs and go through very rigorous testing and a QA procedure, and then try to put it into actually our MapisToDPU libraries. So we operate like almost like a half and half, like a half research and a half a industry kind of thing within my group. We have almost like a 200 servers continuously doing QA testing of all our designs. So that helps us to actually push our designs in a production quality manner to the community. And then on the top, we have this MPI and TGAS support. That has been the traditional support for the MPI. But through that, we are able to also deliver the DL, ML, and data science applications. So let me share some of the very latest numbers we have. We made a 237 release, MapisToDPU 237 release last month. If you were on the mailing list, you would have got a note about this. This is a little bit prior to that, the MapisToDPU 236, but the numbers remain the same. This is on the AMD Milan with Infiniband SDR 200. So as you can see here, like this is the intra node. Within the core, we are able to deliver almost like 190 nanoseconds from core to core. Intranode bandwidth, we are able to go into 42.47 gigabytes per second. And internode on this platform, these are connected with ConnectX-6 SDR. So we are able to go around like a 1.85 microsecond latency internode. And bandwidth-wise, we are able to deliver the HDR bandwidth. So that is like a point-to-point, but when we design the MPI library, we holistically take a look at all the different functionalities, because when you are trying to run an application, you are not just using point-to-point, you are using collectives, you are using DPM, you are using blocking, non-blocking collectives, all the features we try to focus on and try to optimize. So here are some of the optimizations. It has been there in the MapisToDPU library for last few years, are the blocking collectives. We have done a tight integration with SARP. I think Jitin mentioned about the SARP earlier. So these numbers are taken on Frontera system at the Texas Advanced Computing Center. So as you can see, this is it has been taken on the full scale system, like a close to 8,000 nodes. We are able to run it on a full scale. So as you can see, this is the MapisToX, that is the software-based solution. But once we are trying to integrate the collectives to the SARP, we are able to significantly reduce the time. Like an MPI barrier, here you are able to reduce like a factor of 9, factor of 5. Here it is reduced by a factor of 6. So those are with the blocking collectives, and recently we have done similar kind of optimization with non-blocking collectives. And non-blocking collectives are actually getting a lot of prominence these days. If some of you are not familiar, when you are trying to do blocking, let's say I try to do a blocking all-to-all, unless the all-to-all finishes, the CPUs are still idle. I mean, they might be participating in the communication operation, but they are not doing any additional computation. Whereas if you are trying to do non-blocking, you can actually initiate the non-blocking operation, and while the operation is taking place behind the scene, you can actually compute further. Okay, so that means you can actually exploit overlap of computation and communication, and that is very, very important. And here, as you can see, we have done a lot of optimizations together with the SARP logic. This is available with the MapisToDPU. So the green lines, as you can see here, we are trying to show the overall time, like the time for communication together with computation. That means if the number is lower, that means we are able to give you the overlap of computation and communication, and the right hand side is trying to show the percentage overlap. So as you can see, compared to 236 version, we are able to actually reduce the latency and also increase the overlap. So that means that will help your overall application performance. This is for I barrier. This is for I all reduce. We have also taken care of similar things for other collectives. Now, with the last release, we also provided support with Rockport Networks. Some of you might be familiar. There's a new network which is coming into the market, which has been there for last 2 years. So we have done a tight integration of our library with Rockport. This is already available. So here, as you can see, this is also kind of a latency. Here we are getting like a 3 microsecond latency for small messages, and the bandwidth wise, we are able to go like around 10,000 megabytes per second unidirectional and 20,000 for bidirectional. So then the other network which is coming in the market is the Slingshot. As you know, Slingshot has 2 versions. Many of the current deployments are Slingshot 10. That is the numbers I'm trying to show. Very soon we'll have support for the Slingshot 11, which will be actually the network which will be used in on the Frontier system and a lot of other upcoming systems. So here we have done some very detailed evaluation with not only our MapisToX library, compared with also OpenMPI and the CRAM pitch. So as you can see here, again, in the intra-node numbers, as you can see, like we are able to deliver like a 0.22 microsecond. Bandwidth wise, we are able to perform comparable to other stacks. And inter-node, we are able to, over the Slingshot 10, we are able to give like a 2.55 microsecond. So these are all the point-to-point. We have also started optimizing some of the collectives. As you can see here, these are small scale numbers based on the availability of the machines, what we had access to. Like in a 4-node 64 ppn, like a 256 core experiments, as you can see, MapisToX is able to deliver very good performance for MPI bcast, MPI all reduce, compared to other stacks like AMPitch and OpenMPI. So we are continuously been optimizing these, and once we get access to larger scale systems, we'll be very happy to bring some of the results to you. And those are some micro benchmarks numbers. We are also working with a lot of application developers. Here, there is some of the performance numbers from the HEFFT team. This is from the OCRIS, running on the OCRIS Summit. It's a parallel 3D FFT application. As you can see, here MAPITch is able to sign very well compared to the other libraries. Similarly, this is another example of Idaho National Lab. So they have been using a lot of end application for nuclear energy research. So there again, we are driving through the MapisTo libraries to deliver the best performance and scalability for their applications. So those are the basic CPU results. I'll come back to GPU results a little bit later, but let me also introduce some DPU. I'm sure you must be hearing a lot about this Bluefield DPU, which you can think of like it's an advanced secretary. Okay, just like think of executive and secretaries, the host processor, if we can think of executives, the DPU has ARM core, so you can think of these are active secretaries. So how we can take advantage of that to really offload MPI functions? Okay, and especially for non-blocking collectives, I gave that example earlier. There I showed the CPU-based results, but if the non-blocking collectives can actually be offloaded to the DPU, then you can actually truly achieve overlap of computation and communication. So that's what we have been working on. So these are like your host processor executives, and these are your secretaries. So the question is, instead of host trying to exchange information and trying to implement the non-blocking collectives, can we actually offload to the ARM cores? So here we have a library which is MapisToDPU. This is actually being developed through Icicle solutions. It is based on the MapisTo 236, so it is a derivative of the public version from the OSU side. We made a release in February this year, just 2 months back. So this actually has all the supports for the MapisTo 236, and also it has all these non-blocking offload, MPI, AllToAll, AllGather, IBcast. And this is actually being used in the ISC 2022, the student cluster competition. So they have been giving also this library to explore how to exploit these DPU capabilities for other applications. So here, let me show some sample numbers. I'll just start with AllToAll, especially AllToAll, non-blocking AllToAll is very demanding. So here, as you can see, those of you are familiar, like MPI, we have a eager protocol and rendezvous protocol. Eager protocol typically uses copy, so you don't get a lot of overlap. Sorry, you get overlap, but the rendezvous uses the RTS CTS, so you don't get overlap. But this is where you can see, if I offload to the DPU, we are able to almost give 100% overlap. So that means when we can run some applications, we actually can benefit it. So here we are trying to show the OSU AllToAll, and this is a part of the OSU micro benchmarks. Many of you must be familiar with that. We have a standard benchmarks which evaluate the computation communication overlap and excuse me, the total execution time, compute plus communication. So here you can see the red lines are MapisTo, and then the green lines are MapisToDPU. The lower is better. Here we are trying to show the communication time. So this is on a 32 node 16 ppn, 512 core runs, and here it is 1,000 core runs. And as you can see, as the message sizes are becoming larger, we are able to almost offload it and get a very good overlap, so that the AllToAll at the non-blocking AllToAll level, we are able to deliver performance benefits like from a 17% to 22%. That is on a 32 node just at the AllToAll level. But now let's go into the next layer, which is application. So here we actually worked with San Diego Supercomputing Center. They are the developers of the P3D FFT. So we worked with them a non-blocking version. So earlier they had a blocking version. So we worked with them the non-blocking so that they can rearrange and then try to put the computation while the non-blocking operations are going on. So as you can see here again, this is 512 core runs. This is 1256 for different grid sizes, 1K by 1K to 1K, so to 2K by 2K to 4K. At the application level, we are able to give benefits of like 18%, 20%. This is on 16 nodes. As the system size increases, these are 32 nodes. Similar kind of improvements we are trying to deliver. You can see 21%, 16%, 18%. So it shows a lot of big potential for offloading this kind of non-blocking collectives to the DPU architecture. So that is for AllToAll. Similar things we see for AllGather. Here again, as you can see, the benefits are even higher, 48%, non-blocking Bcast, similar kind of things we are seeing, 57%, 58%. And also we have done with iscatter. This is not available with the latest release. This will be available in the next release. But here we are able to go even up to 60%, 64%. So at a micro benchmark level, we are able to demonstrate these benefits. So the next question is how to show it at an application level. So we are exploring some applications, but I would like to indicate this to the community. If you people have some applications where you want to change your blocking collectives to non-blocking collectives, we'll be very happy to work with you to trying to see how much benefits we can actually try to see with the new DPU architecture. So if you are interested in this kind of studies, please send me a note, and we'll be very happy to talk to you. So those are on the CPU and GPU side, but let's, sorry, CPU and DPU side. Now let's move into the GPU side. As many of you know, I mean, the GPUs have been there for many years, and many of you might have heard of this term CUDA-aware MPI. So in fact, this is the concept we introduced from my group in 2011, almost like 11 years back at ISC. We did a joint collaborative work with Mellanox and NVIDIA at that time, being separate. We tried to bring those GPU direct RDMA. And the broad idea is that if the GPU and the Infiniband are sitting next to each other in the PCI bus, instead of taking the data from GPU to the host and sending it, can we directly send it through the PCI and the network itself? So it shows a great potential, and this concept has been very widely now adopted into a lot of other MPI libraries, even other like a Icicle and all the other libraries, MLDL layers. So you see the lot of benefits. This is, for example, is without the CUDA-aware MPI support. Now you can see with CUDA-aware MPI, this is on a x86 platform, we can send data from GPU to GPU on another node in 1.85 microseconds. In addition to GDR, we also use libraries like GDR copy, etc., loopback. There are a lot of techniques have been used to really cut down on this latency, and that gives to also very big boost in the performance with respect to bandwidth and bidirectional bandwidth, and that gives the boost into the application performance. So we are continuously trying to even optimize that further and further, using that CUDA-aware MPI concept. So this is the very latest design, which will be available in the MapisToDPU GDR 237. It's not there. It has just been accepted to be presented at the SCW workshop in conjunction with IPDPS next month. So here we are focusing on AllToAll V, that is the vector variant. And a lot of applications actually use AllToAll V. So again, the question is how we can optimize that using this CUDA-aware concept, both intra-node and inter-node. So here we see like again across the teal line is the new design. This is actually in a log scale, the y-axis. So even though lines are closer, there is a very big gap. You can see in a one node, there is a lot of dense systems are coming, like this is an 8 GPU systems and 16 nodes of these 8 GPUs. We can actually, based on the message sizes here, if you see on like a smaller message sizes compared to Nickel, we can give actually 13x improvement for this AllToAll V. Even for large message sizes, we can give you like a 20% improvement on these systems. And we have actually studied this on two different cases here. One is the HEFFT library, HEFT library I indicated earlier. So here you can see if you can optimize the AllToAll V, it is able to on a 1024 cube, we are able to give you like almost 5.4x improvement on within a node. And once you scale it to 128 GPUs, you get almost like a factor of 28 improvement in performance. So it shows like this CUDA-aware concept, if we can really optimize and use those things to optimize and bring all the collectives to the bare metal performance kind of things, you will be able to see a big performance boost for your applications. The next thing what we are been working for the last 2 years with the respect to GPU is the on-the-fly compression. I mean, traditionally GPU have been used for, let's say, computation. You put a kernel, you do the computation. Some of the collectives we actually have designed the kernel-based collectives to optimize, like a reduce and all reduce. But here we are going the other approach, that when you are trying to do communication, many times the GPU cores are idle. So why don't we take advantage of the GPU, those idle cores, to compress the data before sending it? Okay. So on the sender side, we'll do a compression. Of course, it will take some time, but if the compression ratio is good, on the receiver side also, we'll put a little bit of overhead on the decompression, but overall, the message size which is being sent is reduced. So we'll get good benefits in latency and then the throughput. So this paper was presented at IPDPS last year. It was a best paper finalist. And when we talk about this compression, we are trying to make sure, I mean, there are different solutions available, lossless, lossy, but here we are trying to take like a lossless compression. And in fact, looking at an application like AWP ODC, which is a earthquake simulation, the end application is still, I mean, through compression, we are able to provide the final kind of a the simulation. We are not disturbing the execution or the stability kind of things. Just purely using compression technique, we are able to deliver. You can see 18% to 35% better in terms of throughput, and in the reduction in the latency, like a 15 to 26%. So similar things. So that was based on point-to-point. Next, we have actually taken the same ideas for compressing the collectives themselves. So this is just a paper which got accepted. We'll be presenting at the ISC 2022 in June. So here we have tried to, instead of doing point-to-point compression, I mean, if you have point-to-point compression, of course, all-to-all will get benefited. But here we are actually going and implementing all-to-all in a compressed manner within the library. And as you can see, here we have two kind of applications we have evaluated. This is a PSDNS, which is a traditional scientific application, and here it is a deep speed, which is for the deep learning environment. So here you can see like up to 64 GPUs, 256 GPUs, we can give you like a 29% benefits in terms of latency. And here even in the deep speed, we are able to give like a 35% improvement. So these designs are coming in another 2 weeks. We estimate to push this MapisToGDR 237. So please wait. And then if you have this kind of applications, you will be able to take advantage of that. So then, so all these results I talked about NVIDIA GPUs, but we are also, as you know, the other player in the field is the AMD GPUs, and then the Intel GPUs are coming. So we also now have support for the AMD GPUs in a very unified manner. So this is through the ROCm software. So it's a ROCm aware MapisToGDR. It has been there for last few releases in our MapisTo stack. So here again, we are comparing MapisToGDR, the current version, latest 236, and with an OpenMPI. And here, as you can see, we are able to, this for intra-node GPU to GPUs, we are able to deliver like a 1.75 microsecond latency, and inter-node it's around 4 microsecond latency. And this is trying to show collectives. As you can see, all DUs we are able to significantly perform better, both on the like all reduce and bcast compared to OpenMPI here. Now, these are the very latest numbers. Now you can think of that Slingshot 10 I indicated earlier. Now Slingshot 10 with AMD GPUs, we also get very good performance. So this is again the MapisToGDR 236, which is publicly available. So if you have this kind of systems access, you should be able to reproduce the same numbers. So here you can see this is the GPU to GPU intranode. We are able to deliver latency of 2.68, and here point-to-point internode, we are able to deliver like a 4.28 microsecond. And collective side, here in fact we compared with also Icicle, that is like the equivalent of Nickel from AMD. And as you can see, like compared to Icicle, other libraries, we are able to deliver also very good performance on collectives. So these are like some of the very latest samples numbers I'm presenting on the MAPI side to help on the CPU, GPU, and DPU. Now let's change the gear a little bit, and here I'll be talking about how we can take advantage of our library for high performance deep learning and machine learning also. Excuse me. So here, what we have done a tight integration of our MapisTo library through these intermediate layers. Some of you must be knowing this horrible torch distributed and deep speed. And then a lot of end users actually use these frameworks like TensorFlow, PyTorch, MXNet, etc. So through this tight integration, what we are trying to do, both CPU-based deep learning and GPU-based deep learning, we are trying to actually make them integrated so that the end users, you don't have to change anything. Okay, as long as you can put our stack here, which is in this case is a MapisToDPU driven infrastructure, you should be able to actually really see a boost in application performance. So we have this project, High Performance DL. If you go there, there is a very detailed user guide. How do you download our MPI library and integrate it with the other stacks to get advantages. So this is the kind of the convergence I mentioned earlier. We are trying to take a look so that as long as you have your just MPI library installed on your system, you will be good. You should be able to handle both the traditional HPC as well as the new AI workload. So let me show some numbers, performance numbers, starting with data parallelism, and then I'll talk about a little bit of data and model parallelism with out-of-core DNN training. I'll give an use case, which is a AI-driven digital pathology, and then I'll also give some examples for the QML kind of environment. There also we have done tight integration with our MPI libraries. So here, these numbers are CPU-based training. I know a lot of people focus on GPU-based. I'll show those numbers. But even if you have access to CPU-based systems, you should be able to take advantage of those. So here, these are some numbers from TAC Frontera. I introduced that system earlier. So here we are running ResNet 50 on 2,000 nodes of the TAC Frontera. Each node has 56 cores. So overall, you can see like almost 115,000 cores. And we are able to actually train ResNet 50 in just 7 minutes. Okay, which is very impressive, just purely utilizing CPU cores, not GPU cores. So it means that even if you have like a CPU environment, you should be able to run your AI workload there. On the GPU side, we have similar kind of things. So these numbers are taken on LASSON, which is a Lawrence Livermore National Lab system, 256 voltage GPU. And here, again, we are trying to compare with the Nickel, which is available from NVIDIA, and then we are comparing with our solution, our MapisToDPU GDR. And here you can see almost like based on this distributed framework, you can actually achieve almost 10,000 images per second faster with our MapisToDPU GDR integrated stack. Now, those are the numbers with pure data parallelism. But as you know, the model sizes are continuously increasing. And as the model size increases, you cannot fit the entire model into the GPU. So it's very hard to do data parallelism. Here we are trying to show like a kind of a rough outline. If your input image sizes keeps on increasing, depending on how much memory you have for GPUs or CPUs, once you cross that, these are the region, the light green region, you cannot run data parallelism. You have to run model parallelism or some kind of hybrid parallelism. So we have come up with this solution called HyperFlow, which is a hybrid parallelism. We presented this paper at ISC 2020. It's also available in the archive. So if you use this kind of a model parallelism and the hybrid parallelism here, like on the CPU systems, here we are trying to do a ResNet 1001 training on 512 nodes. You can see we get almost a speed up of 481. Okay, on a 512 nodes with a 94% efficiency. That's very good. You can really try to run very large scale models here. Similar kind of things we also see on the GPU side. The same framework is running on a ResNet 1K on 1000 GPUs, voltage GPUs, and we are able to run it with a 97% efficiencies on GPUs. And these are some different our internal solutions, but the final design, as you can see in this green, we are able to really deliver very high images per second training. Now, as as you know, the field of the deep learning is continuously also moving, starting from the very CNNs, they're going to transformers, and all the newer models are coming up. So we are also trying to see how these newer environments and newer networks can actually be optimized on the modern systems to give very good performance for training. So here we have taken, we call it like a subgraph parallelism for transformers. We call it super. So you think of like a simple example in any DNN, you see a lot of these examples. So now the question is, if I have like let's in this example, like a 4 GPU, how do I distribute this graph properly in an optimal fashion so that these kind of things, which are the communications, we can minimize. And if we can minimize that communication, we'll be able to get a boost in our training. So this is the paper we presented last year at IPDPS. And as you can see, this is how we are able to accelerate the transformer models. If you take a look at this compared to data parallelism, here we are using that super parallelism, we can get almost a factor of 3 improvement. So that means we are able to train your things by a factor of 3 faster on 1,000 GPUs. So those are some of the studies. Now let's try to link it with actual and application. So here we have been collaborating with some of my colleagues at OSU who are actually pathologists. So as you can see, like the pathologies means when we go to doctors, the doctor may prescribe to have take some pathology test with blood, urines, etc. And typically they are produced in slides, and then the pathologist takes it and then tries to narrow down the disease. But these images gradually are changing in the sense these images, if you take a look in trying to do it in a digital manner, it's like 100,000 by 100,000 pixels. Okay. And especially when a pathologist looks at some of these images, they spend some time, like let's say 10 minutes or 15 minutes. Now the question is, can we use actually deep learning to narrow down that kind of an analysis so that the pathologist, instead of spending 15 minutes, can actually spend 3 minutes to perform the analysis? And every hospital has thousands of these slides every day they are generating. So here we are working with OSU Hospital trying to see how we can actually try to apply our DL techniques to come up with the training. So when we started collaborating with them, they were actually running on 1 GPU. Okay, so with the 1 GPU, it was taking almost like 32 hours. So we did a very quick study with them and then trying to do a scale up. And then with the different solutions, we were able to reduce to 4 hours and then trying to do the scale out. And then here we were reduced to almost 0.46 hours, like 27 minutes. So we are able to reduce from 32 hours to 27 minutes. So overall, we're able to really deliver 15x reduction in their training time. And they are very quite happy with this collaboration. We presented actually this result at SC20. So now you can think, I mean, if you are an end scientist, I mean, instead of waiting for 2 days or 1.5 days for your model training to come back, now just over a cup of coffee or over lunch, your model is trained, and then you can keep on introducing new hyperparameters, do some more searches, or make your models more complex, and that will really help the productivity. So that is actually on the deep learning side. Similar things we are trying to do for the machine learning, which is the QML, that particular stack. So what we have done here, we have introduced this MPI for Pi, and we have integrated with the MapisToGDR library. Okay, so that all your QML applications can now actually run faster. We made this release last year. You can take a look. It is available from the HiDL page. Now, if you take a look at some of the common QML benchmarks and applications like k-means, linear regression, nearest neighbors, truncated SPD, here we are comparing with Nickel from NVIDIA. Compared to that, you can see not only we are able to reduce the training time, we are able to give you almost a speed up of 1.6, 1.2, 1.4 kind of things. So once again, I'd like to highlight that integration, tight integration we are trying to do, so that if your MPI library is optimized, now in addition to accelerating your HPC application, you will also be able to accelerate your ML applications, DL applications. So as the solutions are coming from the OSU side, of course, these all solutions are available. As some of you know, there have been a lot of demand to provide commercial support. And this is where a few years back, we started this commercial spin-off called Icicle Solutions. So there are different basic support, whatever is available, like MapisTo, HiBD, HiDL. We are able to provide the support, commercial support with a lot of optimization, debugging, with a good turnaround time. And we are working with many national laboratories and international supercomputing centers. And while we are going there, we are also trying to add some value-added products. People have been requesting, I talked about this MapisToDPU earlier, but we have another package coming based on Icyle AI. So this is, I showed you some of the AI numbers earlier based on MapisToGDR, but now here we have been able to go to the next step For example, this Icicle AI package now has a integrated profiling and introspection support, support for scalable checkpoint restart. So like this, which will make the end users more and more practical. So for example, here Icicle AI has this deep introspective capabilities. As you know, in all these deep learning applications, the performance of your already used matters a lot, or let's say AllToAll or BCAST. So while the job is running, can you actually see through a dashboard? So here, just like our car driving through a dashboard, online you can actually get a lot of information saying, for example, you see the already used latency, there is a jump here, there is a big jump here. So that means something is not optimized under the hood. So very quickly you can diagnose this kind of performance issues. And also you can take a look at the call sizes, saying there are a lot of calls are happening with this message size, and see that latency is higher. So this is the part of the weakness, and you need to optimize the stack. And you can optimize that stack, then you will be able to even boost your performance of your training. Then also in the DL training, as you know, it takes a lot of time. So this is where people have started now using the checkpoint restart. So here we have been working closely with Lawrence Livermore National Lab. Some of you might be familiar. They have this scalable checkpoint restart called SCR. So we are working with them to have a customized version. We call it SCR Exa. And here you can see some initial numbers. So this is the PyTorch distributed training time. As the number of GPUs are increasing with a very low overhead. In this case, you can see PyTorch has a naive checkpoint restart scheme, but as you can see, as the number of GPUs increases, your overhead keeps on increasing. Sometimes even is 50%. But with our scheme using the SCR, we are able to actually reduce it to 10% overhead. Okay, so that you get the most benefit from your underlying system. And this is especially beneficial for cloud environments, because cloud, if you see, you are providing a lot of overhead for your checkpoint restart. You are actually paying for all those storage and the execution time. But if you can use our solution, you will be able to actually finish your jobs faster, and your total cost of ownership for your cloud runs will be reduced. So I just gave an overview there. If some of you are interested in those products, please feel free to contact us, and we'll be very happy to work with you. The last part, I'll try to take the last 10 minutes to provide you an overview of this new NSF AI Institute. So this, if some of you are familiar, like a National Science Foundation is the big agency which funds research in universities. So they started this new initiative. How do you design the next generation AI frameworks or solutions? And they have funded so far 8 such institutes. We are one of them here. This is a $20 million funding for 5 years. It is called Intelligent Cyber Infrastructure with Computational Learning in the Environment. It's a very long word, but I have a very nice short video I'll play in the next slide, and I hope the audio will come out well. If not, please ping me. So I'll introduce the project through that video and then go into some of the details later on. Okay.
A policymaker wants to know how land use policies will affect a region's biodiversity. A farmer is concerned about how new weather patterns will affect crop yield, while food distributors and public health officials are concerned with how supply chain disruptions will affect deliveries of nutritious foods to communities. Current technology can provide data and models to tackle grand challenges such as biodiversity, conservation, and agricultural and food system resilience. But it still lacks the infrastructure to link across data and models seamlessly to answer complex questions from diverse stakeholders' perspectives. Even AI experts are challenged to create standardized solutions across domains because a standardized cyber infrastructure integration with AI just doesn't exist. Enter Icicle, intelligent cyber infrastructure with computational learning in the environment. Icicle is an institute dedicated to building a national AI-driven computational infrastructure that functions as a utility, much like our electricity, water, and transportation infrastructure. This new utility will enable the delivery of AI to end users with the flick of a switch, enlightening solutions for imminent problems of national, regional, and local importance. Icicle will provide an operational rationale and framework for a cyber infrastructure that delivers wide and easy access to smart computing, plus a conversational interface that allows stakeholders from diverse domains to ask questions and receive answers informed by currently available data and knowledge. For example, food distributors, emergency food agency managers, and logistics company executives might ask, which food supply chains will likely be affected by an approaching storm? The Icicle conversation agent might respond with, I will predict future states of your regional supply chain under forecasted weather scenarios and evaluate alternative scenarios. Okay? Upon confirmation, Icicle would then retrieve satellite data on weather, connect to weather forecast models, acquire inventory data for food producers, processors, distributors, transportation networks, wholesalers, and retailers throughout the region. Use AI models to forecast supply chain conditions from a baseline and alternative logistics that maintain consistent food supply for vulnerable populations, and estimate supply chain disruptions based on historical and current data from other locations, mindful of privacy. Icicle will go even further by accessing high-performance computing centers to backcast and learn how reconfigured landscape-scale precision agricultural production and distribution systems could integrate with alternative supply chain infrastructure to avoid similar future disruptions. Using an orchestra of smart cyber infrastructure elements, Icicle produces a symphonic answer that improves outcomes for diverse stakeholders. Icicle holds the potential to transform today's AI landscape from a series of fragmented tools for use by a few to one where democratized AI and integrated plug-and-play architecture empower diverse end users with knowledge and data flows that are science-based, traceable, transparent, reusable, and trustworthy. Introducing AI for CI for AI. AI for everyone.
So thanks a lot for listening to the video. As you can see, this is a very ambitious project. So think of like a 2030, another 8 years, or even 2035, another 13 years. How do we bring AIs to the masses? So that's what is the focus, democratize AI. You saw one example like a supply chain manager asking these questions, but think of like a very simple, like a, let's say, farmer is trying to take a decision how to fertilize the field. Currently, I mean, let's say there is some disease, might be the disease is taking place only in one area, but the farmer is not able to very quickly detect that and maybe spreading or spraying the fertilizer in all over the places. Not only it is expensive, it is also affecting environment. So can we actually try to run a drone and then get the real-time data and then trying to do the processing and then feed to the sprayer saying, yeah, just spray at this time, or sorry, this region. Okay, so like this, you can think of the same thing, harvesting. The farmer is trying to harvest. A lot of decision is taken whether the market is good or not, how is the weather, if I don't harvest today, if I harvest it tomorrow, can I make more money? So all these kind of things, we want to have AI driven solutions. And on top of that, we want to bring it to the farmer. I mean, see, the farmer may not be knowing how to program a supercomputer or even any command. We want to provide like just like a CD, like a conversational AI interface. So that is where we are trying to put like a democratized AI. So that is the big focus. And then integrated plug and play AI. So think of like how power distribution started like almost 200, 300 years back. These days, we take it granted. I have a device, I have an adapter, charger, I plug it in any place, or in fact, in any country, I expect it to be charged. The same thing we want to do with AI. There are a lot of underlying components, and we want to build them in a standardized manner so that people can actually plug and play and then design their entire environment. Of course, that leads to a lot of challenges, not only technical challenges. I'll show you some of the things. There are also a lot of issues about transparency, trustworthy, privacy. But the broad objective is to solve societal problems. And more importantly, we also want to grow the next generation workforce, because a lot of students currently, let's say, only focused on computer science. So can they actually try to handle some of the societal problems, so that as they become more practitioners, they are trying to take a holistic approach to solve these problems. So this is a big institute. As I said, OSU is the overall lead. I am the overall PI. But there are 14 different universities and organizations participating. There are 46 faculty members, around 60 students. So it's almost like a 120 members team. We are working here on this project. We started on November 1st. It's just 6 months. We will be finishing in this end of this April, but we have 5 years to go. But just to give a perspective here, like all these universities, RPI, Delaware, Case Western, Ohio Supercomputer Center, Indiana, Wisconsin, Iowa, Utah, and then all those things are participating here. And also we have a lot of other collaborators. So just to go inside here, you can see like there are a lot of challenges in designing foundational systems, AI, CI for AI, AI for CI, privacy, accountability, data integrity, even explainability. That is also very important. And this shows a little bit of bigger picture in a technical manner. The example I said, like a digital farmer or a farmer sitting, the data is coming through drones, through sensors, and it has to go through the edge computing, near edge, cloud, through our cyber infrastructure to give that answer in real time with quality of service guarantees. And we have identified, in addition to digital agriculture, 2 additional use cases. One is animal ecology, like how the animals migrate, what is the impact on the environment, the climate change, biodiversity. And also the other one is food security. That is a big issue, as we saw in the pandemic time, food insecurity. There's a lot of things being produced at one place, but a lot of people are going hungry. How do you connect all of them in an intelligent manner? So this is where this is our broad vision. We have to take care of a lot of heterogeneity, compute, context, data, model, interface. So these are the kind of the solutions we'll be working on. At the top is that conversational AI. And I'm very quickly going over just to give you a perspective. To realize this kind of a system, you need to really design a lot of knowledge graphs, where the knowledge is, how they are connected, model commons, a lot of data need to be put together, adaptive AI, federated learning, especially taking data from a different users, and of course the conversational AI. And then from the HPC side, this is where a lot of we focus on how do we enable this next generation cyber infrastructure for AI with high performance training, data management, how to design the edge intelligence, how do we handle it in an adaptive manner to the edge devices, because many of them will be wireless, they may not have enough speed. So how do you decide where to run your computation, where to, for example, do compression or do duplications, all those kind of things. And we also need to have control and coordination. The third angle, which is very important, this is the new field which we're trying to do, AI for CI. So it is not CI for AI, but as the CI is being developed, how we want to use AI to design the next generation CI. So we call it like a AI for today is CI for tomorrow. So that means if we can learn, let's say we are trying to do some deep learning on a model, and let's say there are various CPUs, GPUs available. Can we come up with a model how that execution time depends on those parameters? If we can come up with that, then not only we can predict or design the next generation hardware, but if a request comes for a training, we exactly know where to run it and how much time it will take, whether it is an HPC center or in a cloud, to provide those kind of real time response. So those are the 3 kind of the examples I indicated used in inspired science. So here I'm highlighting actually 2 of my colleagues. In the last 6 months, we already have some of the solutions. This person, he's actually a food and agriculture faculty. Chris is actually computer science. So we are working to do this kind of the pest management or nutrient management. So think of like these different diseases. The drone can fly, and very quickly can grab the picture and analyze, saying, okay, this part of the field has these X, Y, Z diseases. And then based on that, you spray X, Y, and G pesticides. So we can actually, just like precision medicine, some of you must be knowing, has been working. We want to do precision agriculture here. Okay, and like this, the same precision food set, precision ecology, similar kind of things you can think of, like water management and qualities. You can have a lot of sensors in the field, and continuously you can monitor, and you can also fly a drone and then see which part of the field needs how much water. Not just whether it needs water or not, but how much water is needed. And then you can feed that information to some of the smart drainage and irrigation control, so that the appropriate water is distributed. So it will try to reduce the overall cost of food production, and it will also be very impact in the environment and the climate change and all those things. And all these things we want to actually put together the software. So here we are working very closely with the TAC, Texas Advanced Computing Center. They have a team called TAPIS. They have a distributed middleware. And so there we'll be trying to, it's a different complexity, like some of the light ones are already there. We'll be making some minor changes. The dark ones are some newer, more work will be needed. And then the orange ones are the totally new. We are trying to put it. So the overall idea is that we'll be able to actually distribute or make this kind of a releases, just like you think of MAPI's releases we are doing, we'll be able to have Icicle software releases, and so that people will be able to utilize this. So with this, I'd like to conclude. Again, this is the first time I'm presenting this in the HPC AI advisory, because this just project has started, and we are of course looking for a lot of collaborators from industry. We'll be soon putting together an industry affiliate program, and also other universities, students who would like to collaborate with us. We'll have a faculty affiliate program also. So those are in the pipeline, and as it evolves, I'll be able to bring those to you. So we are looking forward to collaboration here. If you are interested, please again send a note to me, and we can. I'll be very happy to discuss. So with this, let me conclude here. I started with a very broad vision of upcoming exascale systems and clouds need to be designed in a holistic manner. I presented some of the overview of the opportunities. I also presented some of the solutions from my group. But what I am presenting is Icicle is not just from my group, but from this big organization. So I'm representing them, and we are very ambitious here. And we hope that in the next 5 years, we'll be able to really bring AI-driven solutions for masses, and so that the community will get benefited here. So with that, let me thank my sponsors, but more importantly, these are all my heroes. Starting with the MAPIS project, what I presented is like a work of 21 years, and all these people and have contributed here. So always I salute to them. So with this, I'll stop here. I know I took a little bit few more extra minutes. If you have any quick questions, please feel free to ask me over the chat or directly, and I'll be happy to answer. Otherwise, please send an email to me. Thank you.
Thank you, DK. Great presentation as always. Always happy to have you here. The only comment, and it's not even really a question, it comes from Sharon. I think he echoes the same sentiment of a very nice presentation, and again, learned something new today, which that being Icicle. I think we all learned something new. So thank you very much for presenting about Icicle. That was great.
Thank you.
If other questions do come in, I know you're going to be here all day.
Yeah, maybe one question.
Yeah, go ahead, Kilat.
I found the connection between DK Panda and GTIN. I found the connection. And then they think that the connection is in VAPIC, but no, the connection is something else. Essentially, democratizing AI or bringing AI to the masses or making AI as a service requires to develop the digital twins, for example, and all the complex workload that can take the information and provide the insights is needed, right? So that makes AI as a service. To make AI as a service, we need to make supercomputing as a service.
Yes.
And making supercomputing as a service, this is on GTIN's shoulders, right? Because making supercomputing as a service means that It's not just enabling supercomputing access to everyone, but making sure that he's getting supercomputing performance. And this is where the performance isolation comes into the game, and this is the preview that was done on Azure. And here I just connected everything that you mentioned, DK, to everything that Jitin is working on. And essentially, it's everything. Everything connects one to another. Now, after this long story, a quick question. DPUs, just for everyone to know, if someone wants to explore MapisToDPU and start running applications on top of that and optimizing applications with DPUs, how can one get access to this version of MapisToDPU?
Yeah. So thanks, Gilad, first for the comment. I mean, as you know, I mean, everybody is connected. I mean, we are getting connected in a many different perspectives. So there are a lot of opportunities here to work with a lot of people. The second one, MapisToDPU. Yeah, as I said, we have a copy installed in the HPC TAC. So please send a note. I'll just quickly, since this MapisToDPU is from Icicle Solutions, send us a note if you go to the website, and we'll be able to give you a free license. So just send us a note. Either it is on your local cluster, or if you are using it in the HPCAC cluster, it is already, a version is already available. Please send us a note here, this one. Just contact us at iciclesolutions.com, and we'll be very happy to work with you.
Yeah, thank you, DK.
Thanks.
Great. Thanks, Gilad, for that comment and question. DK, I don't have any other questions in the queue, but I'm sure I'll follow up with you if
Sure.
something comes in.
Thanks a lot.
Thank you again.
Thank you. Bye.